Why is there a red light on that cam? Oh, good morning, everybody. You're here. I think I'm live. I think I'm live. Yes, I believe I am. Therefore, I acknowledge the traditional owners of this land, the Whadjuk Noongar peoples. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. So, at the very last minute, I ended up settling on a topic, but good morning to Dogs, Gavin, Iggy is here. Good morning, Iggy. Johnny Begdal, Marty, Michael. Michael who? I don't know. It's just Michael. Crispian is here. Russell, Scott, some call it fun. Stephen. We got both Stephen George and Stephen W, just like last week. Stephen, it was a pity you couldn't make it to the barbecue last time, but maybe you can for the next one, because the next barbecue is this coming weekend. Trady, Sion, Wagon Loads. Okay, it's really good that Sion is here, because I'm sure he is going to have strong opinions about what I'm about to talk about. And Sion's strong opinions are always interesting. They help inform my way of thinking. Mitchell is here, of course. Keith, good morning, Keith. Jordan, David, Amanda, Wagon Loads, Tassie Bob, Todd. Who else is here? Henrik. Yes, Henrik is here, of course. Mitch. Good to see you, Mitch. So this is a topic that I was just talking to Mitch about in person yesterday. So maybe Mitch will have some ideas as well. Sharky, Justin C, Chris is here, Mark, Kim S. Many people in the chat already. So as you can see, there is no Mitch, which makes me sad. But Mitch has other things to do, and we are going to continue our introduction to KiCad stream, also known as John being out of his depth and trying to figure out what's going on. You are live. Thanks, Jordan. Right. Johnny, the model for this emoji is in the room. Where is that? I don't know. Any news on the package? Henrik, no, I have not received anything. Another 5 memberships. Thanks, Johnny. That's very generous. All those memberships going out.
Johnny Bergdahl has gifted 5 memberships.
That's great. Hang on, I've just got to turn that volume up.
Imogen Ann has received a gifted membership from Johnny Bergdahl.
It's going to repeat this a lot. And?
Jordan Reese has received a gifted membership.
Yeah. I'm just going to hit mute on that for a minute, because it is going to announce every one of those memberships, which is really cool. But let's see. Okay, just flipping back through. So David asked about the Starlight satellites last night in Melbourne and whether anybody saw them. And I did not. I saw Facebook posts about it and photos of them. It looked pretty spectacular. It was a very bright, very distinct line, like someone had just drawn a line across the sky. It's weird. It says arrived in your country like it arrived there 12th of February. Okay. I don't know what's going on then, Henrik. That is strange. Okay. So backstory here. There is this little thing that I've just been talking about with Henrik that nobody else would have a clue what we're talking about. The backstory to that is Henrik has ordered something, I think it was on AliExpress, but ordered it to have it shipped to me. And as far as I know, it hasn't arrived yet. And I'm not even sure what it is. Oh, maybe I do know what it is. So, yeah, we're just having a bit of a mystery about what happened to the thing that Henrik ordered for me. Now, okay. Oh, Stephen George said apparently Starlink is again tonight in Melbourne at 9:18 p.m. northwest, but don't quote me on that. I'm going to go to the press and I'm going to quote you, Stephen. I'm going to say, Stephen said 9:18 northwest. Okay, so the topic. Actually, I had better mute my phone just in case. I don't know who that was. That might have been Henrik actually, but I'm not sure. I just got a ding on my phone. So, the topic. Where to begin with this? Now, I have not thought through how to talk about this subject, so I don't have a particular sequence. I have no plan. I'm just going to make it up as I go and try to explain the backstory. So, what I have been thinking about for quite a long time is some kind of a generalized test jig framework. Now, Mitchell said, is there ever a plan? Even when there is a plan, it's not usually a good one. Okay, thanks Henrik. Yes, it's the parcel info. Very cool. I will check that later. Now, over the years, I have made many test jigs for testing products, devices, boards. So, backstory. Let's see if I can find something. PCB test jig. I'm just going to give a very brief background.
I don't know that.
Alexa, stop. Okay, I'm going to bring some things up for those who have not seen these before. This is just, all I did was search for PCB test jig on Google Images, and there are a bunch of these things. Now, what you can see here is a board with a whole lot of pins sticking up. This is a test fixture which has got a whole lot of stuff on it. You can see some large resistors here, there are some ICs on it, there are some rotary switches. There's actually quite a lot on this test fixture. And test fixtures can be quite complicated. Now what you often see is a structure kind of like this. And I'm going to, where is it? I'm going to get rid of my face because it's getting in the way of this. So this is a typical test fixture that you would see in many factories. This is some kind of a double fixture, and it's got this little lever arm on the top. And what you do is have a test jig on the bottom with a whole lot of contacts. You put your PCB into here, you pull the lever, it clamps down and holds it in place and makes temporary connections to it. Here's another one using a laser cut guide to align the board in the correct place, and it's got little relief holes in here so you can lift it out with your fingers. Here's a batch of them. These things are super common. You go into any PCBA factory and they probably have dozens of these things. In this particular case, it looks like they're often called things like bed of nails testers because they have all these little spring pins sticking up that make contact with the circuit board. And in this particular case, you can see there are these spring contacts sticking up, and on the top there are these fingers sticking down, which are used to apply pressure to the top of the board and push it down so that it makes good contact with these pins. And sometimes there are spring contacts on the top as well so that it can contact both sides of the board. So anyway, I've just flipped through a few things here and you get the general idea. I have done many of these sorts of things in the past and I can show you some. There's one in that's a very complicated wiring setup going into that one. And there's one that has a PCB slid in with two little clamps on it, and the clamps have been specifically positioned in this case to sit on the top of ICs so that it's not just pushing down randomly on parts of the board, it's on areas that have a good flat surface. And you can go and buy these sort of fixtures as blanks, and then they get customized with all the spring pins. So the mechanical structure, you can just go and buy one of these. They're not that expensive. How much? I don't know. It's a while since I've looked at them. But if you're in, like in Shenzhen, in China, walking around the markets, typically you can walk up to a stand and buy one of these for, I don't know, 20 bucks, something like that. I'm just making up numbers now, but yeah, it's been a while since I've done it. And then you use that framework to fit all of the custom part of it, which is the test pins and the cable that comes out from it, so that you can then connect it up to your device that runs the actual tests. So the board that you're testing, oh, there's an example of an Arduino-ish related thing. Yeah, okay. So this is typically how I have done them in the past. Sometimes I make a custom circuit board for the test jig, and sometimes, well, one really convenient way to do it, if you've got a really simple sort of test requirement, is you can just use a blank PCB of the board that you want to test, because often the test points will be where there are already connectors on the board, or where it doesn't yet have connectors populated. So what you can see in this case is they've put these little test probes into the holes where the connectors go, and haven't fitted any of the other parts. And then what you can do is just solder jumper wires onto the test probes, and that gives you connections to all of those locations. So when you put a populated board on top of this, these little pins here will make contact with the locations where the headers solder on, and then you can power up the DUT, the device under test. So the DUT is the device under test is the board that you are testing. That's your test victim. So the populated board is the DUT, and that sits on top of this in this case, and then you have connections to ground and power and I/O, etc. on these locations. This only works in simple cases, because often you want to have test probes going onto test points that might be little flat pads under the PCB, and these probes come up and make contact with those flat pads, but there's no hole where the pads are located. It's just a flat exposed piece of copper on the bottom of the PCB, or solder mask, or you know, hassle or whatever, whatever the surface is that hasn't been soldered. So in that situation, you have to make a custom PCB or mount pins somehow in the correct location. All right, unmute the speech. Aha. Okay.
Peter Lawler said, unmute the speech.
Okay, I've unmuted the speech. Okay, so yes, I forgot to do that. Yes, so I've done both of these methods. I have a bunch of examples of things I can show you. In fact, I think I will, because this is going to get to, I've got to reach up high up there. So I've got this box here with some test jigs and stuff in it, and a brochure for a test jig company, which actually is partly what, oh look, there's one of the little where I've got to get it in the right place. Yeah, this is the sort of thing that you can just go and buy in a market. It's a standardized frame. It's got mounting holes and things in known locations. So what you do is you make your own a test adapter that goes into here, and then you just use this mechanical structure to engage it. So you put the board in, clamp it down, run the test, release it, take it out, put the next board in. So yeah, this is totally unmodified. It's just a blank that hasn't yet been set up. And I've done things like this. What is this a tester for? ESP1SH. So this is an example of a custom PCB. In fact, I'm going to, let's come over to here. I'm pretty sure I've shown this before on the stream. The camera is way zoomed in. Let's see if I can unzoom, which, I don't even know which. No, not that way, that way. That's better. So this is, you can see there's a laser cut base. It's for the ESP1 shield. And there is a Freetronics 11 under there, which is like an Arduino Uno. That's what actually executes the tests. Then there is a custom PCB on top, and the PCB has the sockets that we plug in the device under test. So in this case, it would be an ESP1 shield.
Said, good you brushed your teeth this morning.
I did. So then you plug the board in. In this particular case, it's testing a shield that already has headers soldered on, which is why it has sockets here. That one I was just showing on screen a minute ago, the photo, is for testing a board that does not yet have its headers on it, which is why it's got spring pins in these locations. But in this case, it's for testing a shield that already has headers, so it can be plugged into this. And then there is another connector on the top where the ESP1 module goes on. So in this case, there is an IDC cable that loops around, and it's got pins, so that plugs in on the top of the device under test. And then there are 3 LEDs here. There's ready, pass and fail. So there's a green pass LED, a red fail LED. There's a piezo, so I can complain if it fails the test, and a reset. So what happens with this particular one is I put the shield in, I plug this in on top, I press the reset button, which then makes the 11 run its little test routine. It communicates with the device, and then it, so when it starts the test, it lights up the ready LED as it's doing the test, and then it goes red or green depending on whether the board has passed or failed. And then I can take it off, put the next one in, plug it in, press the button, and it does the test again. So this is an example of a custom PCB to make the testing structure. You can see it's got a few parts on it. There are some resistors on here. Now this is years and years ago that I made this. I can't actually remember the details of how this one works. So I think what's happening with this is that it is connecting, I think these are voltage dividers, and then these pins here are connected through to the, yeah, I don't know. Yeah, I think there's a voltage dividers to these pins that come up to the board on top. But you can see in this case, it's just passing directly through, although this pin is cut off. You can see one of the pins is cut off in there, so it doesn't pass it through. And in many cases, what you want to do is not have a direct pass-through of those connections. So what you could do is have a set of headers that are offset, and then some of them would have different connections between them. Anyway, that is one type. This is another one. This is actually for testing PoE regulator modules. And so it is laser cut. It's a few layers stacked. There is a cavity in there that the module fits into, and you can see there are pogo pins sticking up through it, so they just come up through this, and they're at different heights. It's a little bit difficult to see. I don't think you can really see it on the camera there, but the pins are set to be at different heights so that it makes contact with ground and a couple of other pins first, and the power in, the V-in pin, is lower than the others, so when it makes contact, the power in pin is the last thing to make contact. And with this one, it's...
Mr. Lawler said the jig is up.
Yeah, the jig is up. So with this one, and just as a reminder to myself, it's got a sticker on the bottom that says what to do. Apply 32 volts DC to DC jack, measure output voltage. I should have said on there what the output voltage should be, but that's labelled on the module anyway. So these leads just go to a multimeter, and then plug this into a power supply. And this is as simple as a test jig could possibly be.
Seriously, how do you test your testers?
Yeah, well, testing the testers is a trick. That is a bit of a recursive problem. So this is as simple as a tester can be. You plug it into a power supply, you plug it into a multimeter, sit it on the bench, you get the module and you go, juke, 7 volts out, good, juke, 7 volts out, good. You just keep putting them on. So with this is perfectly adequate for testing something like a voltage regulation module, so a PoE module. You don't need more than this. It does the job perfectly well. What else? I'll just show one other example of a test jig. One with pogo pins. As you can see, I have many things here in this box. Okay, this is a good example. I like this one. I've done a few of this sort of jig, similar to the other one I was showing you. So this is for testing free NFET modules, and once again you can see that it's got the Freetronics 11 to run the tests, just mounted on a laser cut base, so it all sits on the bench nicely. And on the top it's got this custom PCB. So this PCB was designed purely as a free NFET tester, and once again it's got test and then pass or fail LEDs. It's got a buzzer to complain if it detects a failure, and on the top it has some pogo pins. Now ideally this would go inside a laser cut structure that forces the module to go into the correct location, but I didn't actually ever get to the point of doing that because this was working perfectly well and I wasn't doing a huge number of devices with this. But you can see here that it's got a couple of large pogo pins which are used for guidance. Oh no, these ones are connected to, yeah, you can get locator pogo pins as well, but these ones are actually electrical as well. So these ones have got larger heads on them because they are connecting to large holes in the module. It's a high current module and it has connections on it that are physically very large, and these little test pins would just go straight through the hole. So it's got some large ones here, then it's got these other test pins, and it has a switch, and you can see that the switch top head is just below the top of the pogo pins, and that is the test start button. So what you do with this particular one is you get the module, you sit it on the pogo pins and push down, and when you push down it hits the button and that triggers the 11 to run the test, and then it gives you the pass or fail output. So you don't even have to press anything to start the test. You just get the module, push it on, get a result, and put it aside. Push it on, take it off, put it aside. So that's a very quick way of doing tests, like automated detection of the board and running the test and then giving you an immediate output. So yeah, for simple things, this does the job very nicely. It's very quick to run. But for more complicated things, it's a different story. Just going to move this back under here because I'm going to show this in a second. It's a little thermal printer that I've just got working, running off a Raspberry Pi, and I'm going to show you, let's see, so I want to show you something on here, but I've actually, funny thing is, I've used this to write notes on, including phone numbers and things of people. But this, so I've got my hand over it to cover the phone numbers. So this thing here, what you can see on the screen there, this is part of a brochure, and it's from a company here in Melbourne called Redback Test Services, and they make these amazing test jigs. And so if you're after high-end sort of test jigs, these people do really good work. Unfortunately, I just can't afford it. So this test system, what you can see here, there is a chassis, and then you can see that there is a section on the top with all of these spring-loaded pins that push down. These are not electrical connections, they are mechanical connections, just to push the device under test into position. The green board you can see there is the device under test. That's the example. And then this, I can't remember if this connects to a computer or if it has a computer in it. I have a feeling that it connects to a computer. And so there is the base chassis and then modules that you drop into it. And the idea with this is you have a common chassis that you can use for testing all of your products, and then you just have a different module that you swap in. So if you have one particular product that you're testing, you build a module for that product, you plug it into your tester, you can run all your tests, and then when you want to test a different board, you pull it out, plug a different module in, and then put your next board in. So if you're doing a large number of tests, this sort of thing is really cool. What it means is that you're only replacing the inset module rather than the entire test jig, which is expensive. And they've got, in this brochure, they've got lots and lots of stuff. Anyway, final assembly automation, many things. So that, where are they? Oh yeah, they're all over the world. Redback is big. Anyway, that was the another way of thinking about this whole problem. I'm just going to shove a few things out of my way and switch back to here temporarily. Now, I don't know if I've actually looked up Redback. Redback. Oh, here we go. Redback test. Okay. So Redback test services. Now, if I could afford it, if I had lots of money, this is the sort of thing that I would do. Sadly, I am not rich, but the way of thinking about this is really interesting. And so where are we? Test probes, test fixturing. Yeah, test fixturing. I think I have a feeling that a lot of this stuff is actually from a German supplier. I think Ingen may be German. Oh yeah, there it is. Made in Germany from Ingen. So this is like top of the range automated testing automation stuff. Very, very nice. I wish I could afford it, but I can't. So I'm taking ideas from all of these different things and trying to come up with something myself that does some similar things. Now, one of the issues with the Ingen test fixtures that Redback sell and set up is the Stephen says, printing a test report for each board as it finishes its test. Yes. Okay, so I will get to that. So there is the cost of the base test jig, like the test system, whatever you call it. I don't know what the terminology is, but the chassis, I suppose. So the test chassis, I'm just going to make up some numbers. They are kind of in the they're in the ballpark, but I'm not giving specific. I don't want to be representing this as pricing for any particular supplier or anything. So say the test chassis costs.
Mitchell R said an FPGA might be a good base due to its flexibility as a standard controller for them.
Interesting. Yes. Yeah, so that's a good thing to think of. Now, say the test chassis costs $5,000. Well, somewhere between like $3,000 and $5,000, depending on the size of the chassis. So if you're testing really large boards or large panels of boards, then you may need a larger chassis, and it might be say $5,000. If you need a small chassis, because you're only ever testing small boards, then it might be say $3,000 for the test chassis. Then you have the module that plugs into it, and the module that plugs in is specific to the device under test. So you need one of those for every type of board that you're going to test. Now this is where things get interesting, because it really depends on your testing profile or your product profile. If you're in a situation where you have 4 or 5 types of boards that you are testing on a regular basis, then it costs you $1,500 for the pin jig for each one of those boards, depending on your scale of production, etc. Maybe that $1,500 is nothing. But if you have, or even more aligned with that sort of pricing model, say you only ever have 2 boards that you're testing, like 2 different types of boards, then it could be worthwhile going down that path. But if you have many different types of boards that you're testing, so in my particular case, I have boards that I'm testing for clients. I have quite a few clients. Each client may have 4 to 7 different PCBs that I assemble for them and test. By the time you add it up, there could be very easily, so this is not even counting the boards that I do for myself, so Superhouse and Freetronics type boards. I would have maybe 30, I think somewhere in the region of 30 different boards that I regularly produce for my ongoing clients that I need to do testing for. And each of those boards would need an entire test fixture. So if the insert costs $1,500, then that's 45 grand worth of those inserts that I would need to buy in order to set up testing for all of those boards, plus the chassis itself, like another 5 grand. So 50 grand to get set up with the test framework to be able to do all of this testing. So and then of course there are my own boards that I want to test as well. So what is so without thinking of any of the specifics of the technology, I'm thinking at the high level here of the the financial breakdown of how this works. I want a system that scales. I'm thinking about the optimization from a pricing point of view. The optimization for me is in keeping the cost of the per board customization as low as possible. Excuse me a second. Sorry, had to cough. Yeah, so the per board part of the system needs to be as cheap as possible because I need many of them. And also there are rapid revisions. If I do a revision of a board for a client and the test locations change, or we need to add a new test point or something, then I need to build a new test fixture, a new breakout for that particular device under test. And if it costs me $1,500 every time to do a new fixture because I've revised something for a client board, it doesn't scale very well. Okay, so Some Call It Fun says, can you control the placement of a set of standard test points similar to a JTAG connector for 80% of the testing? Yes, that's true. Some Call It Fun also said, Wikipedia says one trend is to incorporate built-in self-test right into the board and firmware these days. Yep, that is true as well. And Stephen said, friend made one that used a board edge PCIe connector and the whole panel of boards could be programmed in one hit with the signals routed through the mouse bytes to each individual board. That is cool. Yeah, I've seen that done I haven't seen it done with the PCIe edge connector, although that is a really good cheap way of doing it. I've seen it done by putting test points on the rails, including programming headers. I think there's that little programming header, I've gone blank on its name. It's the alternative to the ICSP header where you just put pads on the PCB and there are some holes and you put anyway, I can't remember what it's called. I've seen programming headers and things on the test rails and then routed through on the panel rails and routed through to the devices on the board. So all of these things are cool ideas and good ways to go about this. So where I'm going with this. Okay. Seeing what Redback have done with the Ingen fixtures got me thinking about this in a slightly different way to what I had in the past. And I like the way that they have done it, because the way that I've done it in the past has been either things like this or complete self-contained things. So when Freetronics boards are done in the factory, for example, it's typically done with a test jig kind of like this, and the entire tester is dedicated to that particular product. So what happens is that when they're not testing that product, this entire test jig goes up on a shelf somewhere in the factory, and they have like shelves and shelves full of these test jigs, one for each of the different boards they produce for their customers. And it can be a fair investment because you've got whatever electronics is used to actually run the tests built into it as well. Oh, this is a thing about making a test fixture. Groovy. That's someone showing how to do it. I'm going to click on that link because, oh, it's a YouTube link. Okay. I'm not going to actually play that right now, but I will check that later. Alright, so I have been thinking recently a lot more about this sort of structure of having a chassis that is the test runner, which includes the computer of whatever sort needs to actually do the tests, and power supply and those sorts of associated things, the general things, and then some kind of a module that plugs in with the test probes and whatever is specific to the device under test. So that's what I have been building. And here. Now you'll see that I've used different names in different places because I haven't actually settled on it. This is one of those projects where I start on it and then it opens, the more I get into it, the more it opens out into an infinite range of possibilities and all the things that it could do. And I ended up getting to a point where I just say, I have to get a basic thing working. It's better to have some basic thing working that's incomplete than to have nothing working and to be chasing my tail on this forever. And
Lawler said, "Hey folks, don't forget to dislike and unsubscribe."
Yep.
For the stats.
Smash that dislike button. So yes. Okay, I'll explain a little bit about how I'm thinking about this, because over the last couple of weeks I have jumped around between totally different solutions to this, and some of them multiple legitimate solutions. So any one of the approaches could be a reasonable way to do it, and eventually this is where I settled on, I just have to do like one thing and try it, and maybe it'll be a disaster, maybe it'll work. So what I started doing was thinking about the types of connections that I need to devices under test. So this is the schematic for the test portion. Now, actually, I'll back up a little bit. I will back up. Before we get into this, I'm going to draw a picture. Am I going to draw a picture? Yes, I think I'll draw a picture. And I can do it. Oh, I have this, I have that. I really should have, oh, I kind of did draw a picture. Here's one I prepared earlier. Okay, let's go for this. It's a very bad picture, and it probably won't make any sense. But let me see if I can explain this. All right. So what I had in mind here is a base plate, like some kind of a, I'll just do like a laser cut base plate, and then at the front of it is a structure with a touch screen on it, and the touch screen will have information about the test that you want to run. So there'll be a screen at like a 60-degree angle, like 30 degrees off vertical, mounted on the front. And there are pros and cons to having. I went through different structures of having it on the side, having it on the back. Anyway, this is what I've got for now. As I said, this is version 0.1, and we'll just see what happens. So what I was thinking of doing for that touch screen is using this. So this is, if I can get this in the right position. So this is a Raspberry Pi with a touch screen, and that is, what is it? Yeah, 800 by 480 pixel touch controller. Yeah, it's a Raspberry, I think it's just Raspberry Pi 3B Plus or something. There's an HDMI loop around that goes from the Pi to the screen. There's a little power supply module which is ripped off. It was glued on. The connections are exposed on there. So the reason I've got all of this mounted is I've got Octoprint running on this, and this was mounted on the front of my second 3D printer.
Scott Miller said 60 degrees is wrong. Must be 57.8 degrees to avoid glare.
57.8. Just looking at this, it looks like it's actually about 45 degrees. So this is the horizontal, and then the screen is angled back. Yeah, so this would be at the front of the test fixture. So there'll be a base plate with this mounted, sitting on it, attached to it. So I've got the touch screen exposed on the front, and then the device on the test goes on the test jig, just sort of above and behind this. So you put the device in under test into the fixture, and then you've got the touch screen on the front that you can use to run the test and see the results, etc. Okay, so that, coming back to my bad little picture here, which is all out of proportion. So that, what I just showed you, is this structure here at the front with the touch screen on it. And then that'll be sitting on a base plate. The base plate I don't think would actually be this big. Proportionally, it'll be smaller, like closer to the edges of the screen. And then behind that, probably mounted up on legs, is a PCB with the test pins sticking up out of it. So this is the location for the bed of nails that the device under test goes into. And then there would also be like a laser cut outline with clear acrylic that goes around it as a guide, like a locating guide. And then what I haven't shown here is possibly one of those clamp arms that comes over the top to hold the board in there. So you drop the device under test into the shape on the acrylic, clamp it down, and it makes contact with all the pogo pins, and then you can run the test from this device here. But the goal is to make this part replaceable so that I can keep the same chassis and just lift out this module and put a different module in order to test a different target device. So if I wanted to put a rack 32 in there, I drop in the rack 32 module, take that out, put something else in there, test something else. Okay, so that's the overall structure, that's the general concept. So that then raises the question of, how do you get the connections from these pogo pins into the thing that is actually running the test and making those connections? And on here I've got a couple of little IDC cables looping from the board here that is part of the test jig down to the carrier board. So that could either be done with IDC cables, or it could be done with like a plug that just goes straight in. So you plug the module in and it makes all the electrical connections immediately. Either way, that can be done. So pogo board is there, breakout cables there, touchscreen. Okay, so what is the electronics? Now I've already shown a Raspberry Pi with that touchscreen. So that then gets us to, let's see, do I have, oh yeah, this was me thinking about different structures. Test orientation, oh yeah, that's a different thing for, anyway. So board goes there, connection. Anyway, that was just me sketching out ideas of how this could all fit together. All right, so, the other thing is that alongside this would be a thermal printer. And that can be plugged in by USB into the Raspberry Pi. So when it does a test, it then prints out a test report on the thermal printer, which is what I've got right here. And we can do things like, in fact, if I slide, I'm just going to slide over. I've just been messing around with the software for this. And if I do, I'm just going to run a script on the Raspberry Pi and we'll see what happens. Okay, so it has just printed a test receipt, a test coupon, and then cuts it off at the end. And it just says, so this is obviously a mock-up. This is not any real test that's being run. So test report shows the device under test, what it is, the hardware version, the firmware version, who tested it, when it was tested, installing firmware, like pass or fail, and then some checks, things that you might have to tick off by hand. So what would happen is that the person who is running the test, there are certain things that the automated tester cannot check, but you need to make sure have been done. So in this case, it's got checkboxes like conformal coating has been applied, yes. The glue has been added to the capacitors, yes. It's got a valve header on it, yes. So you do the manual checks and mark them off here, and then this can go into the anti-static bag with the board. So when the customer gets the board, they get the test report with it, including all of the results of the tests, and there could be configuration options, there could be things like ADC tuning, like calibration values, all of that could be automatically printed on the test report, so you can see what's happened. And the test report would get saved into a database against the serial number for the device. So, where are we? Back to here. Yes. Oh, Gavin says, you watched way too many Thunderbirds in Space 1999 as a kid, Jono. Such modularity. Yes. Mitchell says...
Mitchell R. said it's time to go digital. Print a QR code for each board. Then when you test, you just update the record DB. The other benefit is knowing from start to finish on each board history info, etc.
Yes. Except that I'm not using QR codes, I'm using barcodes, and I have a barcode scanner. So I use, so part of this, by way of background explanation, part of this is that this is an extension of a system that, or a process that I already use. Because I do all of this stuff manually. So this is a way of taking what I do and streamlining it. So what I have is, which one is better? That one. Let's do it this way. So this is a barcode sticker sheet, and this is printed on Avery industrial label paper, which is this stuff. So this one A4 sheet of this paper costs about $8, and it's meant to be close to indestructible. So it's thermally stable. It can be subjected to quite a lot of heat. It's chemical resistant, etc. So you put those barcodes onto the PCB, and it's a permanent record of the serial number. So then I have currently a spreadsheet, but about to become a database, of every board with its serial number, what the device is. So I've got a list of device types. So there's a device type ID, and the spreadsheet lists the serial number, what the device was, who the customer was, what firmware was installed on it, what date it was assembled, what date it was tested, what date it was shipped to the customer, the invoicing information for it, like there's, and also arbitrary notes that go in against it. So I already record that for every single board. Oh, Jordan says, data matrix barcodes are great for storing part number and serial number in the same label. Okay, now, yes, so part of it also comes down to how easy is it to read, and lowest common denominator is barcode, because with a simple Bluetooth barcode scanner, you can scan that and send it to a device like to the Raspberry Pi, so that if I'm going to be testing a board, I can put the board in, zap its barcode, and then the device knows what the serial is of the device that it's about to test. Oh, so many, this sort of thing opens up so many squirrels that you could chase. For example, oh, Jordan says most of those will read data matrix codes as well. Okay. But the funny thing is that most of the time, the serial number isn't actually being read electronically at all. It's being read by a human just looking at the sticker. So what I do is each one of those stickers has the barcode and the number written under it, so you can just read it. Oh, Keith said,
Lawler said too many squirrels are never enough.
never enough. RFID on the board, asked Keith. Potentially, but there could be a space issue and an expense issue. But RFID on the board would be cool, because then I could have a reader in the test jig. Now, all right, so one squirrel that just brought to mind is having the tester identify which test jig has been inserted into it. So there are really going to be two major parts to this. There's going to be the test chassis.
Said whole family of squirrels have taken over a rabbit hole.
Yep, they've moved in. So some call it fun said, random idea for the test module, use a custom PCB with two 40-pin edge connectors that integrate into your testimator board. Yes, and then there's a part number for an AMP connector. That is kind of what I'm doing. So what you can see here in the 3D view, we'll go to for just a second. So my general concept is that this board will fit just behind the Raspberry Pi with the touchscreen. So if we look at this from the edge, the screen would be here somewhere, like on the left side at a 45 or a 57.6 degree angle, slightly overlapping this, so the back of this board is exposed behind it and connected to it. So what's on this board? Alright, so this has a Raspberry Pi Pico on it, and as you can see, a relay, a big power connector, a power switch, some other ICs and things, and I will explain all of that. Well, I'll get into the specifics of this in a minute, because I need ideas, I need inspiration, and I'm sure people here will have good ideas to do things in a better way than I've done them here. Oh, and that's a CAN bus connector. So we've got a row of connectors across the back, and the way what I started doing here was, once again, if I jump back to here, I just sat down and started thinking, what are the things that I'm going to need connections for on this test board? So I want to be able to supply 12 volts to the test board. I want to be able to supply 5 volts to it. I want to be able to supply 3.3 volts to it, and monitor all of those. So I want current monitoring on the power connections going to the device under test. I want digital inputs coming to the input from the point of view of the tester. So digital inputs to the tester, where I read digital values off the device under test. I want digital out, so I can drive pins on the device under test. Analog in, and so that's for reading values between like 0 and 5 volts, so like an ADC input. But also I want what I've got listed here as V-sense in up to 32 volts. So what I might be testing on here is a board, just as an example, one of the water cannon controllers. I might be testing this with a 24 volt voltage source and testing the output of the motor drivers on the board, which means that I want to be able to sense the voltage on a motor driver running at 24 volts. And it could be proportional up to 24 volts. So it's not enough just to have a basic analog input connected to it. I'll need some kind of voltage sensing inputs. So voltage sensing in, CAN bus I might want. So the device here might have a CAN bus interface on it, and I want to communicate with the device under test via CAN bus to verify that that interface is working. Programmable loads. In the case of a motor controller, for example, I might want to have a load connected to it so that I can be pulling like, I don't know, like 20 watts or something out of it or higher, because what I might be wanting to do is have one of those motor drivers running at 24 volts and pushing out, it could be multiple amps. So it could be 50 watts, it could be 100 watts external load, and I need to be able to load those motor drivers up to validate that they are really working. What else is there? I2C. We might want I2C communication with it. ESP flash, I ran out of room on my page here. I might want to flash an ESP32 on here. I might want UART communication because I might want to be able to verify that a comms port is working. So once you start going down this rabbit hole, I started off thinking, oh yeah, it'll only be like digital connections and analog connections and that's it. And then I realized there are all these different things, and then it just starts getting down into esoteric territory like CAN.
Scott Miller said you'll always want I2C.
Yeah. So that's right. So what I've got... oh yeah, so Stephen says you might want analog out to spoof different signal levels to the board on test. Yes, exactly. That is a good point. And Andrew said with adjustable current limiting and ability to turn power on and off. Yes. Scott said, I wonder how small you could reliably make a QR code on a silk screen of a board. Sion said, that's what my test jig does. Each board adapter that the DUT connects to has an EEPROM on it, and the test jig knows what the board it's about to test is. Excellent. Cool. Sion said, plus I can change the DUT on the adapter on the fly, like testing a tiny X board that all has the same footprint. Groovy. Okay. Good stuff, Sion. Yeah, so I was thinking about it being kind of like the way a Raspberry Pi hat works. With the hat standard, it has an EEPROM, and when you plug...
System notification. 1 hour remaining.
When you plug a hat into a Raspberry Pi, it can interrogate the EEPROM and discover what the board is and load the correct drivers, etc. So I was thinking about it something like that, and that sounds like what Sion has done. So Stephen said you might want to have a separate header on the side to break out I2C, SPI, UART, so you can make future I/O expansion boards for this application that require something specialist. Yeah, so that's the infinitely expandable sort of approach to this. Yes. Now, getting into this sort of territory is where I just started thinking I have to just call it somewhere.
Jordan Rees said move your digital I/O to I/O expanders on the DUT test board.
Yeah, so Jordan said move your digital I/O to I/O expanders on the DUT test board. Now that is something to think about.
Scott Miller said this might be the world's deepest rabbit hole.
It could be. This is an entire career. Doing test jigs is an entire career, and I don't intend to make it my career, but it is an important thing to solve. Some Call It Fun also had a very important point, which is, do you ever need to test environment conditions, humidity, heat, cold? How far can test-o-meter be from jig and board under test? Does it even matter? Might be expensive. Yeah, well, that's other part of it. And in some cases, you might need to test vibration. There are so many things. Once you go down this rabbit hole, it is really falling into the hole to eternity. It is, yeah, you could never get out of this hole. And that's why, as I've said a few times now, the more you gaze into the abyss, the more you realize that this is like a mind-blowingly large problem to solve that you can't solve in a 100% universal way. You have to, at some point, you start having to put constraints on it and say, I'm not even going to open that door. I'm just going to keep that closed, focus on what I need to do and solve my problem. Because if you start trying to make this a totally universal thing, it will never end. It'll never be done. So this is my V1.0 compromise. So what I'll do now is show you the compromise that I have resulted in, just so that I can get something started. And then it might be all wrong. It might be a total mistake, and I realize that I need to scrap it and take a different approach, but at least I've learned something along the way. All right. So, yes, John said here for the second half at least, what have I missed, how many squirrels? And Scott says, all of the squirrels. This is one topic which is just nothing but a universe of squirrels. Yeah. Right, so keeping in mind all of this intro that I have given, the context of the different types of things that I want to be able to do, this is what I've ended up with. I went around on a couple of alternative architectures. My first thought was to make the test jig. So this is kind of the thought sequence I went through. I thought of putting.
Unexpected Maker says, and you did it in KiCad right at Superhouse TV?
Sadly, no, because I did this. I've been doing this over the space of a few weeks, and it was just a little bit too soon. Although I do have a version of this board. I did actually last week start doing a layout in KiCad of this, and but I was already well advanced with this in Fusion, and it was at the point where I just need to fab it and see what happens, and then I can do a version 2 with all my learnings from this and do that in KiCad. Yeah. So it's a start. Yeah, you only missed the intro.
Aaron Knox said, seems to me the Pogo daughter board that interfaces with the DUT should be called the Test-O-Mator. This current board is more like the Master Jig board, or let's call it the Master O-Mator.
I'm not sure about that name. Yeah, so right. Yeah, so naming. You can see here, this is Test-O-Mator, because it was like Test Automator was where that came from. And so what am I thinking? Oh yes, okay, so a number of high-level architectures that this could follow. Architecture the first. This whole thing could be run off a microcontroller standalone. So you have a microcontroller.
Said Aaron Knox, it's def the Test-O-Brain board.
Test-O-Brain. The microcontroller that is on this, which could be an ESP32 or an RP2040 or a SAMD or an whatever, it doesn't matter. An STM32, yeah, you could build this board totally self-contained, able to run tests against a target board. Okay, then architecture the second. Have this board just be things like a bunch of I2C I/O expanders and connect to something else, which could be a laptop, it could be a Raspberry Pi, and treat this as a as just like an I/O expansion thing with all of the drivers and stuff for the different types of I/O that we want, and have all the brains in some external, more powerful computer. Architecture, the third, is to use something like a Raspberry Pi and use its I/O to connect to the device under test. And then you get the sort of high-level computer and the sort of low-level I/O sort of munged into one. And what I've ended up going for is a fourth architecture, which is a combination of a microcontroller on the on this test controller board plus a Raspberry Pi. Now, there is a reason for that. There are multiple reasons for that. I know, Aaron. I deliberately, like, I heard it in my head, and that's why I didn't say it. I read it, but I didn't say it out loud. So the what's going on? Okay, now, because I was thinking through the actual sequence, and I realized that there are multiple parts to what I want to do with this, and my idea expanded slightly. I don't want to just be doing testing on the board. I also want to do things like load firmware on the board. Now, in some situations, what you'd want to do is have specific test firmware that you load onto the device under test only while it's being tested. It's not the firmware that you're going to run on it in production and that gets shipped out to the customer. So there might be a two-stage thing where you load test firmware onto the target board, and that test firmware does things like enable a whole bunch of extra debugging. It might exercise parts of the hardware in certain ways that the production firmware doesn't do. It might have communications over a USB serial connection, for example, that gives feedback on what individual I/O pins and things are doing that you don't want to expose in the production firmware. So there may be situations where you load test firmware onto the device under test, you execute your tests, and then you load the production firmware onto it, and then it's ready to go out. So I didn't want to have to load firmware on boards by plugging them into a computer and then unplug them, put them in the tester, and then test them. What I wanted to do is have a brand new board that has never been programmed. It's like straight off out of the reflow oven and ready to go. Put it into the test jig, run the test, have it load the firmware, execute the tests, and pass or fail the board and generate a test report. So having the combination of the Raspberry Pi so the Raspberry Pi could connect to an ESP flasher. Okay, classic situation. A device under test probably will have something like an ESP32 on it with a programming header. It'll have a variety of I/O. It'll have an onboard voltage regulator, so you supply power into it at some, like you might give the board 12 volts and then it regulates it down to 3.3 volts on itself. So you want to be able to test that the onboard voltage regulator is working. You want to be able to flash firmware to it through the programming header. You want to be able to exercise it and see that the board is working properly. Okay, so Aaron said, Pogo board should have a PCIe style edge connector and could hot swap into a connector on this board in replacement of the IDC connectors. Loads of connections for expandability. Yes, that's right. So one way to do that, I was actually thinking ahead slightly with that. Now, in my first iteration of this, what I'm probably going to do is just use IDC cables, but what I had thought was there is no reason that the test board couldn't overlap with this one and have sockets on the bottom so that it simply plugs in on the top of this board. As long as the connectors are in the same location, they're all accurately located, then you could just plug it straight in, no need for cables. So this could be sitting in the bottom of the chassis, and then the test module could plug in on top of this and just plug into these headers, and you've got all the connections and you're ready to go. Okay, so then what do we have along here? Looking at the top of this, you can see that there are connections for different types of I/O. So there is a power connection on the left, which I'll get to in just a second. You can see that it's got 8 pins. That's because it also has I2C on it. So this is like the base connection. The simplest possible thing you would do is have a single IDC cable running from the power header to the power header on the target test board, and that would give you power and I2C, because you pretty much always want I2C, as someone said earlier. And then I've got 2 sets of digital pins, and you can see that these are 10 pin headers, and there are 8 in each of them, because I've got a couple of, was it ground? I think it's 2 grounds in each one. So there are 8 digital pins here, there's another 8 digital pins here, and then we've got analog inputs which go through voltage dividers into external ADCs. I'll show you the specifics of this in a minute, because this is where I need ideas. Then I've got DAC. I've got a DAC here. So I've got a digital analog converter so that I can drive arbitrary output voltages, because I want to be able to simulate different voltages going to the target board. And the reason for that is that boards like, a specific example. One of the boards that I want to test is the water cannon motor controller board. Now that board has inputs for limit sensors. Those limit sensors are Hall effect sensors that sit at 2.5 volts when they are not being activated by a magnet, and then the voltage swings one way or the other. And what I want to be able to do is simulate the Hall sensor input going to the target board by driving a digital to analog converter from the tester. So I want the tester to be pretending to be the limit switch, send a command to the motor driver telling it to move in a certain direction, verify that it is actually turning on the motor driver outputs, and then I want it to simulate one of the limit switches being activated by moving that analog voltage and verify that the motor stops driving, that the controller stops driving the motors. So that's why I've got a digital analog output. Now it's got, this header is set up for 8 channels of DAC, but I actually only have 4 connected, because I've got a 4-channel DAC on the PCB here.
System notification. 45 minutes remaining.
Ooh, Stephen says you could have a PCIe connector and use an extension cable as they are available off the shelf. And Gavin said, or interface at 90 degrees from the front. Some call it fun made a point, which was, what about custom firmware tests for manufacturing, but if applicable, post in production firmware if user holds a button while powering for basic functionality test in the field? Yeah, that can be done in some circumstances. You can have like so post, for those who haven't seen that before, POST is power on self-test. So when you start up a computer, like a PC, typically it'll go through a post, and you can force it by holding down a button while it is powering up. So yeah, that is definitely a valid approach. Now, some other things you can see on here. Now let's just go to, and there's a CAN bus pass through. So in the case of testing that water cannon motor controller that I just mentioned, I need a CAN bus connection to the board, because I want to validate that the CAN bus interface is working, and I want to be able to send commands via CAN bus to move in a certain direction so that I see that it then moves the motor outputs. Oh, Aaron said, are you using the PicoW so you could also create a temporary AP to test Wi-Fi on boards? Not sure if your intention is for this board to connect via wire connection into a Raspberry Pi and screen. Ah, yeah, okay. Interesting, Aaron. I hadn't actually thought of that. So testing Wi-Fi on the target board, that is definitely a valid thing that you want to do. Never even thought of that. Which is embarrassing because I should have thought of that. Don, you made it. Hooray. Yeah, so this CAN connection here, I will explain more in just a moment. What you can see if I switch this back to here is the Raspberry Pi Pico sitting in these headers. The way I envisage this actually working is that I'll put a Raspberry Pi CAN bus shield into the headers first and then sit the Raspberry Pi on top. So this will actually be a little bit higher and there will be a CAN bus shield in between, and then the connections from the CAN bus shield loop down into these screw terminals, and then all that happens is those screw terminals pass through to this header. The reason I've used that 4-pin pluggable 3.81mm screw terminal header is that's what I use on just about all of my boards that have CAN bus on them. It's like my standard thing, which makes everything interchangeable. I can just plug cables in and use the same wiring looms and stuff, and they all plug into that same header. So what I can do is have a cable that goes from there that plugs into the device under test. Okay, let's have a look here just for a second. So we have, this is the test board. So we've got power in. We've got an XT60 connector coming in here. So power coming in through a very large diode for reverse protection, and then we have what have I done here? What have I screwed up? I don't know. I just had a sudden thought that I have just messed all this up. Oh no, that's all right. Okay, so S1. I was looking at this and thinking it was a relay, but it's not. This is the main power switch for the tester. So we have power coming in here, and this will probably come from a lab power supply or something. It's just an XT60 connector going through like a 40 amp diode through a fuse with a power switch. Nothing exciting about that. Now this raises the issue that sometimes I want to supply a lot of power to the device under test. If I'm testing a motor driver and it's running at 24 volts and pulling 5 amps, I need to get a lot of power through to the test board. We will get back to that problem in just a moment because I have a solution for that. So power switch going through a voltage regulator. I've used the LM38020. That should be LM, yeah, I think I stuffed that part number up. Anyway, it's the 2 amp version of the switch mode regulator. So it's got a 15 microhenry inductor on it instead of the 33 microhenry to provide the 5 volt rail. And that can power the Raspberry Pi or whatever. Then 3.3 volt regulator. None of this is exciting. 5 volt sensor. Okay. So I have an INA260, which is it's a current sensor. So INA260s are they're very expensive chips. I think like $9 or something each, $8 or $9 each. But it's an I2C current sensor. I've used these in a few projects. They are really nice. I really like them. This particular one, the 260, has a wide input voltage range. I think it'll run up to 43 volts or something, which is pretty cool. And so what you do is you supply power coming in on the high side. So we've got the V bus connection here and in plus, and then you send the output out to your load. So in this particular case, we've got the device under test 5 volts. So when we want to supply 5 volts to the device under test, it comes from this net, which is running through this chip, the INA260. So what we can do is measure how much power is being drawn by the device under test. Now at the moment you'll see there's no switching on this, which is a limitation, and then the same thing on the 3.3 volt. So taking the 3.3 volt rail and we're supplying that to the device under test through the current sensor. So we can measure how much power is being used by that device. Alright, so Raspberry power, oh, I've already done that. Control power on, I've actually done some of my to-dos. So let's mark these off. Replace SS56 with a high power diode. I've already done that. That was that big diode on the input side. Power control on 12 volt, 5 volt, etc. Outputs to DUT. I've already got it on 12 volts, so I'll take that off. 5 volt 2 amp power to Raspberry Pi. I think I'm going to do that with an external module. And EEPROM on breakout board, so tester can auto load the correct test profile. I haven't done that yet, so let's just save that. Come on, you can save. Come on, give me focus back. There we go. Where are we? Yep, Raspberry Pi power. So that's just passing out power to a voltage regulator module externally, which will power the Pi. Okay, now, here we've got V in coming in, which is typically 12 volts, but it doesn't have to be. So this is the raw voltage coming in from the external lab power supply that would be running all of this show. So we've got another INA260. So we've got 3 INA260s on here. So there's like 25 bucks worth of just in those 3 chips. And then that goes to a relay. So the difference with this one is that we have relay control of the power going to the device under test. So this relay is being controlled by the Raspberry Pi Pico, which means the Pico can power cycle the device under test by controlling this relay. But it can only power cycle the main V in. It can't power cycle 3.3 volts or 5 volts. I could put another 2 relays on there and do that, but that's for a possible future thing. And probably not something I normally care about, because most of the time I'm supplying through VIN to the onboard voltage regulator of whatever the device is. So anyway, moving right along. Where are we? What's this? Oh yeah, so this is Raspberry Pi Pico. It's just the Pico breakout beeper and a status LED, nothing exciting there. And down here, what have we got? Okay, so this is where the interesting stuff happens. And across the top, you can see the IDC connectors. So the power and I2C is the first one. So this is supplying the device under test V in, 5 volts and 3.3 volts, which are those 3 monitored power rails that we were just looking at. There are 3 ground connections, and then it's got I2C. So that is the minimal connection needed to the target. Stephen said I'd assume the tester would be hardwired to Ethernet. Well, the tester could be from the Raspberry Pi itself. So, okay, now in terms of, okay, just backing off, right before I get into all of this, talking about the overall architecture again, just for a moment, like zooming way back out. So what I'll have is the Raspberry Pi on the front with the touchscreen, and that Raspberry Pi will have the test runner software on it and the user interface. Now plugged into that via USB will be the Raspberry Pi Pico, which is doing the I/O, all of this stuff that we can see on the screen here. What that means is that the Raspberry Pi can reflash the Pico whenever it needs to. So if it needs to load a different, we need different firmware on the Pico to run different types of tests, it can be updated. So that could be done on a per target basis. Also plugged into the Raspberry Pi is the label printer. So the the thermal printer that will print out the test report at the end. And then other things plugged in. Oh yes, a programmer. So what I'll do is I'll have an ESP flash programmer plugged into the Raspberry Pi, and that means that I can plug into the programming header on the target board, and then the Raspberry Pi can upload firmware directly to the target board if it's an ESP32. It could also be, you could plug in a USB ASP, you could plug in an ice burner or something if you wanted UPDI programming to, like one of the late model AVRs. The thing is that the Raspberry Pi on the front has these USB connections, which gives us the flexibility of being able to plug these different things in and then have it program the device under test. I could also have it read the barcode scanner. It could use a camera. So we could have a camera in the top of the test rig so that it takes a photo of the board when it's being tested and then stores the photo in the record of the test. And that could also be used, for example, for potentially for color sensing. Say you want to test an LED and you want to make sure that it goes to the correct colors, then you could do some sensing with that. Oh, Quindor is here! Intermittent Tech has made it. Quindor, it's good to see you. I haven't seen you in the chat for a while. Right, okay, so yeah, thanks for coming. Okay, so that's kind of at the high level. So, and someone a moment ago mentioned Ethernet. So the Raspberry Pi could also be plugged into Ethernet so that when it's running its tests, it can store the test results. Like it could push the test results to a database located somewhere. Like I could be running a database, I could have a MariaDB database with a REST API front end on it or something, and have the test runner store all of the test results, push up photos of the tests, etc. That could all be done.
Said plug in a thermal camera too.
That is a great idea, Scott. That I didn't think of that. That is excellent. I have a thermal camera right here. That would be a really, really good thing to do for, yeah, I love that. Scott, you win 10 internet points today. Yeah, because when I'm doing things like running motor drivers, being able to take a thermal image of the board, showing whether the drivers are running hot or not, and storing that with the test results, that's brilliant. Stephen made a very important point. Remember, kids, don't blob photos into your database. Store them on a file share. Yes, that's right. So stick the JPEGs or whatever they are into an appropriate storage and just have a pointer to them in the database, like a reference to the object ID or something. So, okay, to here. All right. Across the top, as I was saying, you see the connections to
System
the breakout.
30 minutes remaining.
And first one, it's very simple. It's power to the device under test and I2C. And then the next one is also very simple. It is just direct I/O connections on GPIOs on the Raspberry Pi. And I thought I should include these. So these are totally unbuffered. There is nothing in between these I/O pins on the Pico. When I said Pi, I meant Raspberry Pi Pico. Nothing between these pins on the Pico and the device under test. Nothing at all. I thought about putting series resistors in here or Zener protection clamps or something, and I decided, nah, screw it. I'm just going to connect direct because I don't know what I'm going to need these for. These might connect to the target board all the way through the pogo pins, or they might go onto circuitry that is on the breakout board, because the breakout board can be more than just pogo pins. It can have its own interface circuitry on it depending on the specific testing that we need to do. So I might want to run UARTs through this, I might want to do all sorts of things. So these are general purpose I/O pins, and they can be either inputs or outputs. between the Pico and the test breakout. And I put 2 ports worth of those, so there are a total of 16. Plus extra, yes. Moving along, voltage sense. Okay, so this is an interesting one, and there are limitations to the way I've done this. These are for doing things like sensing voltages on the outputs of motor drivers. So, and I specifically wanted to have this range so that it could read up to about 32 volts. My most common use case is 24 volts, but I wanted a bit of headroom just for safety. So with these ones, these are voltage sensing inputs that come down. I'll show you where those nets go. So the vsense 0 net, for example, comes down to here. These all go to voltage dividers. So vsense 0 comes in through a 56k resistor, and then there is a 10k pull down as well. And then that is going into input channel 0 on this ADS 1115 analog to digital converter, which I think is a 16-bit ADC with an I2C interface. And it's a 4-channel ADC, so we've got 4 channels coming in. Now, the thing about this is that this is going to bias the line that we are sensing. This is one of the limitations that I am conscious of. Now, the reason, think about this. If we are sensing something, if this vsense 0 line connects all the way through to a signal on the target board, what this is doing is essentially applying a 56k plus a 10k, so a 66k resistance to ground is being applied to the device under test. So if we are sensing a high impedance signal that's at the other end, we could be biasing that signal. This is not a super high impedance input. But I figured that was a trade-off that was reasonable, because my use case for this is going to be measuring the voltage output on motor drivers. And those motor drivers are not really going to be perturbed by a 66k bias when they are, when they're designed for driving fairly high power motors. And then the output of that goes into the analog input, etc. And then we have analog input 0 to 3, analog input 0 to 3. That is wrong. That should be analog inputs 4 to 7. So just got a different I2C address set on those two. The address pin is pulled low on the first one and it is pulled high on the second one. So we've got 2 ADCs running, giving us a total of 8 channels of analog sensing. What have we got there? I2C level shifters. I don't even remember what that's about. 0 to 5 volt analog outputs. Okay, so I've got an MCP 4728 here, which is a DAC. And once again, it's an I2C device. And what this means is that, that's right, that's what it's doing. So this is a 5 volt DAC. I've got level shifters here on I2C. So there is 3.3 volts I2C coming off the Pico, and then I wanted 5 volt I2C for controlling the DAC. And with that, what I can do is drive outputs between 0 and 5 volts approximately. It's a window in between those, because you can't drive fully to 0 volts and you can't drive fully to 5 volts.
Said, I feel most of this should be on a daughter board, since each DUT could have different unique cases.
Yes, Mitchell. Now this is a really important point. I will get back to that in just a second, I promise. Because that is one of the major design decisions that has to be made about this. Okay, so we've got these analog outputs. I've only got a single one of these, so you can see I've got 4 channels of DAC output here. It's a 4-channel device, and up here on the DAC, what I did on the header was I allowed for 8 channels of DAC. These ones actually aren't even connected to anything. In fact, I should put no connect markings on those. Should I, like I can show it if I try to if I rename this one, it knows that there are multiple segments using that net. If I try to rename DAC 7, it knows that there is no other net on that. So the only the first 4 channels of DAC are actually connected. But this is another one of those things
Scott Miller said big stack of daughter boards.
Yeah, this is one of those things where I just had to do something to test that the concept is vaguely on the right track. And this will do for a first draft. This is like a rough sketch just to see if this idea even is worth pursuing, or if I am totally screwing it up and I should rethink my life and not want to sell death sticks anymore. So
Mitchell R. said at Scott Miller at that point, they aren't daughter boards. They're a family.
They're a family, yeah. Okay, so this is, now that I've shown this is getting to the important design decision, which Mitchell brought up about saying most of this should be on a daughter board since each DUT could have different unique cases. Oh, and just in passing, Wagon Load says, are you trying to measure ADC from a long distance? Kind of, yes. It is from a distance of maybe 20 centimeters,
Scott Miller
15
said
centimeters.
daughter boards, sister boards, granddaughter boards.
Yep. DAC stack, says Wagon Loads. Hey DIY, thanks for making it along. Alright, so back to Mitchell's thing about shouldn't all of this be on the daughter board, like on the test breakout? And this is where I had to kind of draw a line, because I could go down the rabbit hole and try to cover every single possible type of test connection for every single possible board and build it onto this incredibly complex test controller that does everything with enough channels to do every possible thing. So I might want 16 channels of DAC and DAC that will do up to high voltages, and yeah, the thing is that it is a never-ending thing to chase and you might want multiple I2C buses. So maybe we want an I2C multiplexer and then break out a whole lot of buses. Like, once you start going down this rabbit hole, there is a lot that you have to put on. And this is where the balance point is of, do you build this on the test controller, which is what we're looking at now, or do you put it on the breakout that is used for each specific device under test? And the conclusion I've come to is that some things should be on, what I want to do is cover some things, the really common stuff on the test controller, on the test-o-mator, and if there are weird oddball things, put them on the breakout. Now, a classic example for that.
Scott Miller said starting to look like it needs to be an actual computer with a bunch of expansion cards feeding into the tester.
Yeah, and that could be, yeah, it could be a monster. And Jordan said, cover the top 80% with the main board and leave the 20% unique stuff on the breakout, Pareto principle. That is exactly my thinking. Now, what I've ended up with here is what I consider to be that 80% common that is going to be everywhere. I want I want digital I/O. That goes without saying. Now, the thing is that these digital I/Os can also, some of them at least, can also be used for analog input to the to the Pico. So like 0 to 3 volt, traditional, just analog read type stuff. Ooh! DIY is now a silver supporter. Thank you. And Wagon Load says, if ADC distance is an issue, use an op-amp as a comparator with analog on plus input and triangle on negative input. Result output is PWM. Yeah, interesting. Okay, so I could do, and then convert PWM back to analog at the other end. Okay, so I could do that on the test breakout. So on the testimeter, the test controller, I've got digital I/O, which is really common. I've got, for me in particular, voltage sensing is a big thing for many of the boards I
Aaron
do.
Knox said this board could have headers with set number spacing, and each module is a daughter board for this board. So this board could accommodate up to 5 module daughter boards, if that makes sense.
It certainly does make sense. Yeah. That's right. So it could be modules plugged in on top of this. Now, because I do a fair bit of motor driver stuff, I need this voltage sensing. For me, that is a common use case. And digital to analog outputs for simulating inputs to devices under test, that is pretty common. And in my particular case, CAN bus, this is a very low burden thing to add, because I did actually consider putting a CAN controller and transceiver directly on this board, but then I decided no, all I need to do is get a CAN shield and stack it with the Pico and it's done. I don't need to complicate this, and if you have a tester that you don't need CAN for, you don't have the shield on it, it's just leave it off. So it becomes like a zero burden addition. The only burden is that I've added this pass-through connector.
Mitchell R. said maybe let me simplify it more. The main board should only contain the core controller. Second can just be I2C but contain the core tests. Then actual daughter boards. Smaller boards, easy and flex.
Yeah. Yes, I think I understand what you're saying, Mitchell, and I agree to some extent. Yes, so there would be plug-in modules that go into the testimeter, and the daughter board, for example, could be an analog input module, and then another board could be a DAC module, and then you could have a voltage sensor or whatever. Analog, yeah. So you could then plug in different things. And maybe that's the architecture. If this was going to become like a super flexible thing that lots of other people are wanting to use in future, then these things could be abstracted out into daughter boards and it could be made a more modular, flexible architecture. But as I've said, I want to just I just need something as a starting point. And so the PCB for this is actually in the air. In fact, I think it might even be in Melbourne already. It's been fabricated, it has been shipped from JLC, and I am just waiting for it to arrive on my doorstep so that I can assemble one, and then I can see if my theories are correct, see if it works, and whether I should take this whole thing further or...
Mitchell R. said NA, simpler. Take what you have on page onto a second board. Later on, if you want to make a Papa board, it's just change one board, not main controller. Also smaller boards.
Okay, just change one board, not the main controller. Yeah.
System notification, 15 minutes remaining.
Yes. Okay, so playing also into this is thinking about use cases and how often... So there are certain boards where I am testing them frequently enough that I will probably build an entire test system, like the testimeter with the Raspberry Pi and everything. So there's probably going to be in the order of a couple of $100 of investment in the chassis by the time you consider the Raspberry Pi and the touchscreen and this board and all of the other odds and ends. Say a couple of $100 to make a chassis with the testimeter on the front. It is probably worthwhile for
Mitchell
me.
R. said so quick and basic to get started like you are, but easy to go forth into the distance later on.
Yeah. Okay. But then I will probably just dedicate that chassis to testing one specific board and never take the test board out of it, like the test jig out of it. I would have that entire test system dedicated to a particular purpose, because there are certain boards that we do in enough volume here that it is worth just having a whole test jig dedicated to it, and then have 1 or 2 test jigs that are set up with the breakout modules replaceable, and they're the ones that we swap on a day-to-day basis depending on what boards we're building. Yes, so maybe this will work. Maybe what I'll end up with is I'll use this first version and just relegate it to being a dedicated tester for one of the boards and keep it for that purpose, and that'll be all it ever does, and then the next version can be for the more flexible one. I don't know, we'll see. So anyway, this board is, I'm going to check, I'm curious. I'm going to pull up JLC and look at my order tracking, because I want to see where it's up to. Order history. So I've got this off screen at the moment just so that I do not reveal customer boards, because I have so many JLC orders. Where are we? Production completed, shipment tracking. Oh, customs. It cleared. Arrived at DHL facility in Melbourne. When? Yesterday. Okay. I'm going to get it tomorrow. Haha! The board will be here tomorrow. So these PCBs are currently at DHL in Melbourne. So they'll go on a truck tomorrow for sure. Oh, Keith is being my quality assurance checker. Keith said, on the board you show 10 amp fuse, but on the schema it shows 15 amps. Yes. Unboxing video, says Wagon Loads. You need to build a test a jig. Jiggity jig. So yeah, on the silk screen it says 15 amps. On the, where is it? T-Place. Yeah. Oh, on the silk screen it says 10 amps. On the schematic it says 15 amps. That, you have some eagle eyes, Keith. Look at that. 15 amps right there. What should it be? 15 amps? 10 amps. Let's make it 10 amps. Let's go for value that, yes, I really do want to change that value, and I'll make that 10 amps.
Cable tie said, never fear. Cable tie is here.
Cable tie is here. Yeah, so 10 amps will do. Yeah, unboxing video. I don't think it's worth doing an unboxing video just for a bare PCB. It's not that exciting. So, come on. Dirt, rat's nest, and rip up. Yeah, anyway. As you can see, this is a 4-layer PCB, just so that I could have neat routing for all of this I/O, because there's a fair bit there. Probably could have, with some effort, I could have forced this onto 2 layers, but who cares? I mean, yeah, could have forced it onto 2, but with 4 I get the benefit of a couple of ground planes plus a power plane, and better shielding and stuff for these signals. So these are being routed on an internal layer with ground plane up adjacent to them, which is nice. So, alright, I feel like I need to pause to take a breath. So 1 hour and 50 minutes I have been talking at breakneck speed, because I've just been trying to brain dump all of the things that I've gone through. So this hour and 50 minutes is just like it is just a summary / brain dump of the process that I've been going through over the last few weeks of working through this and all of the options, what I want it to do. Yeah, it's a surprisingly big project, but I think the payoff is going to be worth it. Tell Scott Miller. Oh, Cable Tie says, I've been listening for a while, got a couple of squirrels, just got to a computer so I can type now. Okay, Cable Tie, unleash the squirrels. Hit, send them to me. Send me
Scott
those
Miller
squirrels.
said midweek stream assembling and testing the tester.
Oh, maybe. Yeah. Also, I just this moment realized I haven't ordered the Raspberry Pi Pico yet. I've got a shopping cart at Core Electronics. Where is it? Core. What have I got in my Core shopping cart? Core Electronics. Because I don't think I have a Raspberry Pi sign in. Yeah, I'm not going to click that show password. Oi, I am showing. Oh, that's all right. I'm doxing myself. I'm showing my address and my phone number, but oh, it's come out of. Yeah, I have no items in my shopping cart. Yeah, this happened to me before. Pico. I need to order. What have we got? Raspberry Pi Pico WH. No, I'm not going to get the H version with headers, wireless without headers. This is what I want. I just want some of these. Let's get some of these. That'll do. Add to cart. And yes, that's what's added to my cart. And there was a CAN bus. CAN bus.
Mitchell R. said, make sure you edit this stream before you make it public on the channel wall.
No, my phone number is already public enough. I don't. Pico CAN, where is it? Precision, not that. GG, not that. Data storage. No. Come on. How about Pico CAN? Pico CAN? Pico CAN. I want the Pico CAN bus shield. Yes, so I forgot that I haven't actually ordered these things that I need.
Said I have a couple of Picos in stock if you're desperate, John.
Ooh, cool. Thanks for the offer, Cable Tie. CAN bus module for Raspberry Pi Pico. There was the Adafruit, this one. This is the one that I want. And let's get a couple of those. With a 7 to 10 day lead time, that's going to suck. But that's okay. Because I can test other stuff in the meantime. Anyway, it's going to take me a while to get this sorted. There's going to be a lot of work in this. So a couple of those. What have I got in my cart so far? All right, I've got a couple of CAN shields and 4 Picos. Yeah, that's what I want. So I need to order those. Otherwise I'm going to be sitting here with PCBs and not be able to do anything. Okay, now we are already at 11:54 and I have not even mentioned one of the biggest squirrels with this whole thing. Probably the thing that is going to take me the most time out of all of it is...
System notification. 5 minutes remaining.
Software. Oh, I say that with trepidation and with fear and trembling. Software. All right, so there is going to need to be code running on the Pico, which I'll probably do in MicroPython, and that will drive the I/O. It'll talk to all of these devices, and then the Pico will talk via USB back to the Raspberry Pi. Now, then the Raspberry Pi will need to have the high-level test sequence figured out. So what I have in mind here is the Pico is essentially going to be a funky smart I/O expander. It's going to need to be able to talk CAN bus through the CAN bus shield, and it'll also need to be able to drive digital outputs, read digital inputs, etc. Do all of those things and pass that information back to the Pi to be able to interpret. So in the Pi, I need to be able to configure things like, it's basically going to be like a flow chart or a sequence of things, like tell it to drive this output high and then watch this input and see what happens. And depending on what the input happens, flag a fault or not. So it's going to have to accumulate the results of a whole lot of little subtests as it goes. Wagon Load says, how difficult is it to reach the USB cable around the onboard relay? That'll be okay. So I did actually think about that. If we go to here, the USB cable will just clear this relay. Yes, I considered that one. It does look like it's close, and it is close. The cable will run, like the USB connector will be right here, but it should fit beside that relay. So the software is going to need to do a bunch of things. It's going to need to present a user interface on the touchscreen so that you can press a button to begin the test. It needs to understand what the tests need to be. So the thing is that this test software could be a whole big modular framework stack sort of thing in its own right. This is going to be a big project. It needs to be able to do things like load a test sequence or know what the test profile is for a particular device under test. And okay, that's a very good point. Some call it fun, say a bit late, but does a test-o-meter board need a piezo to call your attention if something bad is happening? Yes, and that totally slipped my mind. As you saw on the test jigs that I showed at the start of the stream, I do normally put a piezo on those testers so that they can beep if they have an error, and I didn't include one on this. Totally overlooked that. I think maybe, well, the Pi doesn't have a speaker on it, but at least it can show stuff on the screen. Let's add this to the to-do. Piezo. See, there's already needing a new revision for error alerts. Okay. Yeah. Okay, so it needs to do a lot. It also needs to then compile accumulate the results of the tests that it's done, so that it can print out the test coupon at the end to shove in the bag with the board, which could include things like the values read from the ADCs when it's reading inputs. Like if it needs to do voltage calibration, it should keep the calibration values and print those on the test receipt. So lots and lots of things that the software needs to do. And
system notification. Stream is over.
Wagon Light says, can you bodge a speaker into this circuit? Yeah, I could. I could bodge just a 3.3 volt piezo into it, no problem. So I could patch it onto this board. I just need to dedicate an I/O pin to it. Yeah, so as I said, the software, what I've shown you so far is just the hardware, which in some respects is the easy part of this. The software is huge. So it also needs to do things like connect to the central data store where I'm going to record all of these test results. Actually, talking about that reminds me, this is not the right place to put it, but I'm going to put it in here because it's
Scott
open.
Miller said RPi can send text to Alexa.
Oh, you just woke her up. Yes, so the RPi could do all sorts of things. It could do an alert through that way. Thermal camera connected to Pi, and GB camera connected to Pi. So I'm just putting those in. Oh, I just hit escape instead of enter, and it just undid. Got to put it in again. Thermal camera. That was a brilliant idea. Connected to Pi, and just a regular RGB camera connected to Pi. There, I hit enter that time instead of escape. Yes, so a thermal camera mounted directly above the device under test, looking straight down on it. That is a really cool idea. All right, so back to the reason that came back into my head is the software. So the software needs to be able to do things like take a snapshot from the camera connected to the Pi, take a snapshot from the thermal camera connected to the Pi, and push those to some central testing location. Now, all of this can be stored on the test jig. This is one of the advantages of having a Raspberry Pi directly on the jig. Instead of just relying on a microcontroller to run the tests, but having like a full-blown Raspberry Pi on the test jig, it means that you've got local storage on the SD card. So it can you could even run a database locally if you wanted to. So all of this test information, it could all be stored standalone on the test jig. But the thing is that I want to be able to get that information off and push it into a central data store, because this is the potentially dangerous thing. I want to expose some of that information to my clients so that they can log in and see it. So I don't want this information to be trapped on the test jig. I want it pushed to a portal where my clients can log in and enter the serial number for one of their devices and see the full test report, including things like photos of the board. And to do that, I need that in an internet connected thing. So what I'm probably going to do is have a system set up on a VM. Like I normally use Linode. I mean, there are plenty of them around. This is not an ad for Linode, but things like the Superhouse site runs on a Linode VM. I've got a few VMs there that I use for different purposes. So what I can do is push all of this test information into a database, like a MariaDB database running on a VM, and push all of the photos and things that are taken into a data store there as well, and reference it so that clients can come along to something like dashboard.superlab.au. So yes, I have superlab.au registered, the domain name. Right now it's aliased to superhouse.tv. It goes to the same place, but for this production stuff I'm probably going to use superlab.au. So there could be something like dashboard.superlab.au that my clients go to, they log in, they can see all of the boards that I produce for them, click on a board, see all the test results, etc. Right. Oh, g'day to Jack's Tech.
Peter is hangry. 5 minutes ago.
Moo. Right, okay. I think I'm going to go. This has been, amazingly, I've actually stayed on topic. This has been a topic of squirrels, but I have stayed within the same family of squirrels for an entire 2 hours. What is going on? Right. Stephen, oh, that's a lot of RAM. Stephen is getting new fun hardware to run virtual machines on. Okay. What am I doing? I am pausing because my brain has run out of fuel, and I think this is a logical place to actually wrap it up because I've just been rapid fire brain dumping for 2 hours. Ecognito says, prefer PostgreSQL to Maria or MySQL. Okay. I have extremely little experience with Postgres, and lots of experience with MySQL and MariaDB. So just from a comfort point of view, it's the tool I know, so I would probably, my automatic thing without even thinking about it would be to reach for MariaDB, but it is possible that Postgres would be better. I don't know. And Incognito also said would possibly use SQLite on the Pi. Yeah, so many options. I think the data store, like the database specifically, is a relatively small part of the problem, because once you've got some kind of a connection to the database and you can do inserts and queries and things, then the particular database doesn't really matter that much. And I'm not dealing with vast amounts of data in terms of things like numbers of records. We're talking about thousands of boards here, and each board having like in the order of a dozen tests that are run on it. So we're talking about tables that'll have in the order of tens of thousands of rows, and it's mostly just going to be like bits of text or integers or something. So we're not talking about really big databases here that need lots and lots of performance. Alistair said, the biggest issue with MySQL is it encourages poor design. If you use referential integrity in foreign keys and a table type that supports it, it sucks less. Okay, cool. Yes, that is a valid complaint. Right. Oh, Imi pointed out, I totally forgot about this. I believe the next barbecue is next Sunday, the 10th of March. That is correct. Next Sunday is the next Super Lab barbecue. So if you're in Melbourne, please come along next Sunday to the barbecue, starting nominally 12:30-ish, just so that I finish the stream and then take a deep breath and prepare myself for the next few hours of lots of people. So text, oh, long weekend in Victoria, is it? I don't even know when there are public holidays because they don't apply to me. Oh, okay, this is an interesting one. Some Call It Fun said, no, it is not a dumb question. This is actually an excellent question. Does it does it ever make sense to switch the ground leg of the main power along with the VCC? I notice it is always connected through. Is that a benefit? That is definitely something that is worth thinking about. Now, what it also opens up is better isolation and control between the tester and the device under test. Because one thing you'll notice, and I kind of half pointed this out earlier, is that what we've got here is, for example, this 3.3 volt regulator is, no, actually, I'll do something different. I'll look at this one as this is a better example. So we've got 5 volts coming in here. We've got a 5 volt regulator up here. So we're generating a 5 volt rail on the tester meter. Now, if we want to pass that 5 volt rail to our device under test, it comes down here through VBus, through this current sensor, and it goes to the device under test. Now, what happens if there is a solder bridge on the device under test and it dead shorts this DUT rail? What will happen is that it will effectively dead short the 5 volt rail on the tester. We are not protected. This is all exposed. And yes, I know this is a design flaw. It's one that I'm aware of. And it falls into the category of things that I know need to be resolved. But once again, I just need something as a starting point so that I can test whether basic things work. And that is why here I have, well, it's kind of wrapped up in this to do, which is power control on 5 volt and 3.3 volt outputs to device under test. Really, if we are supplying power to the device under test, it should be on a dedicated voltage regulator. Like we should have a dedicated VREG generating a 5 volt rail which goes to the device under test with current limiting, so that if the device dead shorts, it only affects that rail, it doesn't kill the tester. So at the moment, effectively, the device under, this is a good way of thinking. Is there any way that the device under test can kill the tester? And right now the answer is yes. The device under test can kill the tester by dead shorting its power supply, which is bad. But as I said, it's just, this is like a first draft of the thing. I don't expect that this design is not final. It's not even close to final. This was, I've got to just send it off for fab, try it, see where it explodes, see where the smoke comes out, and then I can fix it and improve it. But ultimately the goal is, it should not be possible for the device under test to kill the tester. Right now it can, and I know it can. Scott says all power coming from the device under test need to have some sort of protection as well. Exactly.
Scott said this is version 0.0.1.
Yeah, that's right. Oh, Stephen said could always put polyfuses in for basic short circuit protection. Yeah, that's true. I could put a polyfuse in there. Like, it probably wouldn't fire quickly enough to save the tester from browning out. I think the tester would still probably brown out and reboot or something. But yeah, that's a possibility. So that sort of protection needs to be built into it. All of that can come in future. Effectively, you could have like a programmable lab. You could have multiple programmable lab power supplies incorporated into this. So that is actually one thing I thought about, is doing a super version of this. What you would do, this is really crude. This is just bringing power in from an external power supply, regulating it to 5 volts, regulating it to 3.3 volts. These are fixed rails. What I really should have is variable programmable power outputs here, where the tester can arbitrarily decide what it wants. So it could say, this is a power rail to the device under test. I'm going to set it to 5 volts and I'm going to apply a 300 milliamp current limit. You know, just the way you would set up a lab power supply, you program them in. Like when I'm bringing up a board for the first time, like a new design, I plug it into a lab power supply, I set the current limit to what is a reasonable limit so that if there is a short, it'll hit the limit and nothing bad will happen. Like I don't do it with a 10 amp limit or something set on the lab supply when I power up a board for the first time. I might set it to like 200 milliamps or whatever is appropriate. So effectively what we could do is have multiple lab power supplies.
Peter is super hungry. 15 minutes ago.
Yeah, we could have multiple lab power supplies built into this tester, giving us arbitrary controllable outputs. But that's a big task. So once again, it was one of those things of, that would be the dream, that would be really nice. But for now, this is just, it's going to get me past this first hurdle and we'll have something to revise. You need something to revise as a first thing or you're never going to get anywhere. Okay, I definitely need a rest now. I need to take a pause, take a deep breath, think about life, and then go and watch Dune. So that's what I'm going to do now. I'm going to have lunch, and then...
Scott Miller said system notification. Peter can starve until John is done.
Yeah, that's right. Peter can starve. I don't even know if Peter is here. Has Peter jumped into the chat? Which means we can keep going all day. Yeah, so my daughter has not seen the first Dune movie yet, and I don't mean the Peter Lynch Dune. I mean the most recent Dune, and she wants to see it before we go and see Dune 2. So, which I'm really excited about. I can't wait to see Dune 2. So we're going to watch Dune Part 1 this afternoon. And then, yeah, David T says Dune 2 is a masterpiece. So I have heard. Everything I have heard is that it is mind-blowing. So, anyway, we're going to watch Dune Part 1, and which I've already seen, to get us into the starting position to watch Dune 2 sometime soon. So, Stephen W said fuses and input-output protection could also just be part of the slave test board, as they are cheap and application specific. Yeah, that's a really good point. I could just put it on the breakout. Okay, one thing I have not shown you at all is I have actually designed a breakout as well that goes alongside this. The breakout board with the pogo pins that the device under test plugs into. Now, I've designed it for a specific client board, and I can't show it to you, sadly. But I will show you that in a future thing. That in itself is a whole thing. So I will show you that in a future live stream as we progress with this project. And yeah, there will be multiples of those that I have to do. So I'll show that
Mitchell
and the design considerations. Alistair said the best Dune 2 is the RTS from the late 90s. Really? Okay. Oh, is that a different Henrik? Do we have two Henriks in the chat? Oh, yes, we've got a Henrik from Denmark, and we have a Henrik from Estonia. All right. Okay. I am really going to go because my brain is fading. The squirrel is running out of nuts, and I'm done for the day. So, thank you very much. Also, thank you for all the suggestions. And now that I've got your brain into this sort of mode and you're considering testing, over the next week, you are going to be thinking about this. I promise you. It's going to be in your head. And as you have more ideas, don't forget them, because I want to hear them. Because the way these things get better is I present you a problem and then people give me solutions. And we end up with something cool at the end. So thank you very much.
Scott Miller said, thanks, John. Awesome stream.
Thank you, Scott. And Mitchell said...
Mitchell said, we're going to test you next week.
Test me next week. Yeah, so I'll see a bunch of you next week in person, and the rest of you on the stream. So thank you very much. Have a fantastic weekend and week coming, and I will talk to you all later. Go and build something awesome.